Okay, we're going to talk about curl, how to compute it, a few properties of it, some theorems related to curl, and then we'll talk about divergence. Let's consider the vector field F. And let's say that F is defined by P times I plus Q times J plus R times K. Okay, in this case, P, Q, and R, those are functions. So those are functions in terms of x, y, and z. They're not constants. Then, curl of F is going to be the following. What is this first symbol? Gradient. So we're going to cross gradient with F. And what form will our answer be? A vector field. A vector field. Okay. Importance of curl, it's related to the rotational properties of fluid at a given point. So we'll look at a quick example. We are going to find the curl of F for the following vector field: xz, comma, xyz, comma, negative y squared. So curl of F, we're going to take the gradient and we're going to cross it with F. So we'll have our I, J, K. The gradient is partial with respect to x, partial with respect to y, partial with respect to z. So this will be partial with respect to x, partial with respect to y, partial with respect to z. And then our three functions. Okay, so we're going to ignore this row and this column. So you take the partial with respect to y of this function, partial with respect to z of that function, and you subtract them. So it'll be negative 2y minus partial with respect to z, so that's xy. Ignoring this column and that row, it's a middle one, so that'll be a negative. We're going to have to switch the sign. So if you can picture ignoring those. Partial with respect to x of this function, so that'll be 0. Partial with respect to z of this function, so that'll be x. So then we ignore the row in the column that k comes in. Partial with respect to x, so we get yz minus partial with respect to y, which is 0. So our curl of F then will be, I'm going to factor out a negative y, you don't have to, but negative y, we have 2 add x, then we just have x, and then we have yz. And that is our answer. So again, we said this is a vector field. Okay, do we get the gist of how to calculate curl? Yes? I don't have another example, is that okay? Okay. Theorem that's related to this, bless you, bless you. If you take the curl, the gradient of little f, you are going to get the 0 function, or the 0 vector, rather. Now, one thing that has to be true in order for this theorem to apply is that function f must have continuous second-order partials. Okay, bless you. Because it's fun, let's prove that this theorem is true. So if we take the curl of the gradient of some function f, curl is the gradient crossed with whatever you're taking the curl of, which in this case is gradient of f. So that's a cross, not an x. Okay, so let's actually compute that. The gradient part is partial with respect to x, partial with respect to y, partial with respect to z. Gradient of f is the partial of f with respect to x, partial of f with respect to y, partial of f with respect to z. And then we actually are going to compute this. So ignoring column and row, we get the partial with respect to y of this function. That will be the second partial of f. And then it's partial of y, partial of z. Minus, going this direction, that is the second partial of f. And this time it's partial z, partial y. Middle sign has to be flipped. So in this case, we get partial x times this one. So this is the second partial of f. And then we get partial x, partial z. Going this way, we get second of f, partial z, partial x. And then the last one, if we go this direction, we get the second partial of f, partial x, partial y, minus second partial of f, partial y, partial x. Now, is this going to be 0? And if so, why? I mean, it has to be right, because that's what the theorem says. Why is that equal to 0? In this case, why are all of them equal to 0? What's continuous? Right. Because those second order partials are continuous, like we said in the beginning, those are all going to be equal. Do you remember vaguely mentioning that?
Do you always flip the sign of the second?
Yes. Okay. That was a fun proof, wasn't it?
Yeah.
That wasn't too bad, right? So like that would be a good one for a test, maybe. Oh, so then the logical question here is like, why do we even care about this? Right? Why does that theorem matter? Here's why. If f is a conservative vector field, then we know that f is the gradient of some function little f. You guys agree? So we have a potential function. If we take the gradient of that potential function, we should get our vector field. So the theorem also says the following. If f is a conservative vector field, then the curl of f is going to be the 0 vector. Remember, because f is equal to the gradient of some little f, so that'll be big F, so the curl of big F then will get us the 0 vector. Okay, important question for us. Does this help us prove that f is conservative? So if I take the gradient, or rather the curl of my vector field and I get the 0 vector, does that mean that f is conservative? No. So the theorem goes this way. It does not necessarily mean that the opposite is also true. Did you guys learn at some point, if P then Q, if Q then P? So if I were to work backwards, what is that called? Do you remember? it's the converse. Yeah, the converse. Do you remember those? Inverse, converse, contrapositive? Which one is always true? Don't remember?
That was eighth grade stuff.
Contrapositive. Contrapositive will be definitively true. Yeah. Okay. This leads us to another theorem. That is going to go against what I just told you. If F is a vector field, defined on all of R3, whose component functions have continuous partial derivatives and the curl of F is the zero vector, then F is a conservative vector field. So I asked you before, if curl of F is 0, do you know that F is conservative? And we said no. Well, now I'm telling you we do. Bless you. But it's because I gave you a theorem telling you that that's the case. So your vector field has to be defined on all of R3, which most of the time it is. Component functions have to have continuous partial derivatives. Most of the time that's true. If you find the curl of F and you get 0, then you know that F is a conservative vector field. Okay, we are going to show that the following vector field is y squared z cubed I plus 2xyz cubed j, add 3xy squared z squared k, is conservative, and find the potential function before what we did, so not in 16.4 but in 16.3, we looked at vector fields in 2 space, something like this, and we used the conservative field test. How did we show in 2 space that this vector field was conservative? Okay, partial of P we did with respect to what? And partial of Q we did with respect to what? Okay, remember that? Okay, that applies in 2 space. This is in 3 space. That's not going to work. So now what you're going to have to do when you're in 3 space, you're going to use that theorem above. So we need to show that the curl of F is 0. How confident are you that you can find the curl of that vector field? I think we can do it. How confident are you on finding a potential function? Okay, I want you to do it. So take 5 minutes. Yeah, you're doing this whole question. This is all you. Did we get our curl to be 0?
Yeah.
Okay, good. How are we doing on the potential function? Okay. Do we need another minute or two, or we're ready? Could anyone answer me? I said, do we need another minute or two, or are we ready? We're ready? Okay. I want to show us to make sure that we got what we were supposed to be getting. Here is what I did for the curl of f. So you should have gotten 0, but I want to make sure we got all the right terms. That one look okay? Okay. Next, here's what we should have done for the potential function. That ends up being your potential function. I started with partial f, partial x. Is that where you guys started? Integrate with respect to x. Your constant is in terms of y and z then. I then chose to take the derivative with respect to y, which you set equal to the derivative with respect to y from your vector field. You then integrate with respect to y, which just means your constant is in terms of z. With me so far? Okay, so then take the derivative with respect to z. That ends up being your potential function then. As you can see in red, I have a few notes for you. On your WebAssign, this is always going to be 0. And then you integrate and you just get a constant. That's not always the case though. So the ones that we've done in the notes haven't always been 0, and in your packet, they're not always going to be 0. So just don't get tricked into thinking you're always going to get 0. Other thing I've told you before on WebAssign, they take k to be 0, I think.
It lets you put a k though.
Oh, it does let you put a k? Okay, there we go. How do we feel about curl? Good? Good news is that divergence is even easier than curl is. Oh, I know, fun. Okay, next up is divergence. Divergence of f is going to come when you take the gradient and you dot it with f. Now what divergence of f tells you, so curl of f, we said, was the rotational properties of fluid. Divergence tells you the way in which fluid flows toward or away from a point. So let's actually see what this looks like. we are going to find divergence of f for the vector field that we used in example number 1, which was xz, xyz, negative y squared. Okay, so I already said above, divergence of f is when you take the gradient and you dot it with f. Gradient of f we've already written. Partial with respect to x, partial with respect to y, partial with respect to z. We're dotting that with f. So we are taking the partial with respect to x of the first function, which is z, partial with respect to y of the second function, which is xz, partial with respect to z of the last function, which is 0. So divergence of f then is z add xz, and that's our answer. Okay, one thing I want us to know is we've already noticed when you take the curl of f, your answer is a vector field. This is called a scalar field. So that's important to know. When you take divergence, you're always going to get a scalar field. When you do curl, you're going to get a vector field. Any questions on divergence before we talk about two other things? Okay. Next thing that we need to talk about is what's called the Laplacian. Laplacian is another operator. Looks like that. Okay, it's exactly what it looks like. So gradient squared, you take the gradient and you dot it with the gradient. So this will be the second partial with respect to x plus the second partial with respect to y, add the second partial with respect to z. If we applied the Laplacian to some function f in terms of x, y, z, we would get the following. Laplacian of f is going to be the second partial of f with respect to x, add the second partial of f with respect to y, add the second partial of f with respect to z, fun fact, this is the divergence of the gradient of f, which should make sense. Gradient of f, that's the partial of f with respect to x, y, and z, and then we're taking those partials again. Okay, that's the Laplacian. Sound good? Okay, last thing we need to talk about is how all of this relates to Green's theorem. Okay, Green's theorem we covered when we had a vector field that was in 2 space, not 3 space. So let's consider a vector field that's in 2 space. Let's say that it's pi at qj, remembering that p and q are functions and not constants. Let us suppose that all conditions for Green's theorem are satisfied. Then we saw the following. If we had a closed curve C of f dot dr, another way to write that was the line integral over the curve C of p dx plus q dy. And we saw with Green's theorem yesterday another way to express this or to calculate this was the double integral over the region R partial of q with respect to x, subtract the partial of p with respect to y, dA. So none of that should be new, right? That's what we did yesterday. Well, just for fun, let's find the curl of f. So we have I, j, k. We have our partials. So this is p of xy, q of xy, and 0. Okay, so if we find curl of f, ignore this column, this row, we get the partial with respect to y, which is 0, minus the partial with respect to z of q of xy, so that's 0. This one, ignore the column and the row, we get the partial with respect to x, which is 0, partial with respect to z, which is 0. Ignoring here and here, we get the partial with respect to, sorry, this way first, x. So this is the partial of q with respect to x minus partial of p with respect to y. With me so far? Okay, how that's going to lead us, or where that's going to lead us, is we can rewrite Green's theorem. So we had line integral over a closed curve of f dot dr. This is the double integral over the region R. Okay, we have this right here. So that partial q, partial x minus partial p, partial y. That's curl of f. But when we found the curl of f, it's a vector. We don't want a vector. So what we have to do is we have to dot it with k. Does that make sense? If we take a vector and dot it with k, we're now going to have a constant, or in this case an expression. It'll no longer be a vector. Yeah. Which is that. Isn't that so cool?
Yeah.
Didn't you really enjoy that?
Yes.
Okay, I have, well, first of all, do you all have any questions on curl or divergence? This wasn't that bad, right? Like, it was a lot of theorems, but that was kind of it. Alex?
When you're showing what's curl and divergence and stuff, is that way you write out just like curl parentheses?
I would like if you would write something like this. So give me the general formula and then you can jump in. Does that answer your question?
So divergent is like how fluid flows towards and away from a point. What does curl?
The rotational properties of the fluid at a certain point. That is the furthest that my knowledge goes. So if you have any other questions, don't ask me.